In this video, we're going to hone in on the domain and range of a function. So we already defined these to be the domain as the inputs of a function or the independent variable. So this is typically what we call the x. And again, the variables are arbitrary. You can use whatever you want, but the common nomenclature is to use x for the inputs in the domain, and the range then are the outputs or the y values, or the f of x values if we're thinking of them as a function, right? So either the y or the f of x values. So we are often very concerned about the domain of a function and less so about the range, but still somewhat. The reason for this is that the domain is determining what x values are allowed to be put into the function. What are the possible inputs? And this is of concern for us because we're often, we are the ones putting something into the function, right? We are choosing those values. We're deciding what values we're going to use in this function. So we need to be aware of what values we're allowed to put into the function. The range is of less concern because this is kind of taken care of by the function, right? So if you kind of just think of this like a machine or something, right? Or you have your function and you put something into the function, which would be the input or the x's, and the function spits something out, right? Which is the output or the y's. And this is going to be your range, would be all of the possible outputs. And then the domain would be all of the possible inputs. So we're more concerned about the domain because we're on the input side, right? The function is taking care of that output side. It's taking care of that range. So typically, and it's also kind of hard to find the range without being familiar with how the functions behave already or having the graphs of the function. But it is easier for us to find the domain mathematically or algebraically. So we've essentially looked at two ways that we could define a function, either as just a set of ordered pairs. So let's look at like the function f of x equals 1, 3, 2, 4, 5, 6, for example. So just like with the relation, the domain here is just going to be the x values and the range will be the y values. And when it's just a finite number of ordered pairs like this, we can just list out all of the possible f or x values, right? So the domain is going to be the set of numbers 1, 2, and 5. And the range is going to be the numbers 3, 4, and 6. And typically we write them in increasing order. It doesn't really matter though. So the domain defines all of the numbers that can be put into the function. So if we try to put a number outside of this, outside of the domain into the function will be undefined. For example, if we tried to do f of 0, well, 0 is not defined in this function. There's no y value for an input of 0. So this would just be undefined. Okay. So this is all nice and laid out when we have a finite number of points like this. But what happens if we have an equation? So let's just use, we haven't used a different letter yet, so let's use g of x, for example, equals x plus 1. X can be any value here, right? It can be any number. There's no reason it couldn't be. So we're kind of just looking for, is there a reason that we couldn't put an x value in here? Assuming that there's no context here, because the domain will be context specific, right? If you're working on a problem that involves like length, for example, you can't have a negative length or a negative height. So in those contexts, it might be different. But in this abstract sense where we just are looking at this function in a vacuum, there's no reason that x can't be any number we want it to be, right? Because all we're doing is we're taking x and we're adding 1 to it. And we can add 1 to any number we want to. So the domain here will be, we would say, all real numbers. So the real numbers is a specific set of numbers which encompasses pretty much all of the numbers that we encounter. There's some other sets of numbers, but we'll just get into them if they come up at all. But for now, we're just working in the real numbers. And there are some other ways that we can write this. Sometimes we might write this symbol, which is like an R with like a double line on the left side of it. It's a little hard to hand draw, but if you look up the all real numbers symbol, it should come right up. Or we use what's called interval notation. This is the most common way, probably, to write this. So in the case of all real numbers, first of all, in interval notation, we write, it kind of looks like an ordered pair, but it's read a little bit differently, which is that we write the first number that's possible in the domain, comma, the last number that's possible. In this case, all numbers are possible, so there is no first number. So we would instead write negative infinity, meaning that we could go all the way down, negative 1,000,000, negative 1,000,000,000. You just keep going all the way down through the negatives. You would never reach the end. And then the highest number then would be positive infinity, which we just write as infinity. Okay. And then these parentheses on the end here, these indicate whether or not that number is included in your domain. If there's a parentheses, it means it's not included. We always use a parentheses with infinity because infinity is not a real number. So it would not be included itself in the domain. We can't input infinity as one of our values. Let's go ahead and look at one where there actually would be a restriction. Okay. The simplest example here would be if we have the function h of x equals 1 over x, 1 divided by x. The restriction here is that in general, we can't divide by 0, right? Division by 0 is undefined. So there's no way that we can let x be 0, right? We can divide by any other number we want, but x can't be 0. So our domain here, we could write all real numbers except 0. Like sometimes you just write it down in words, but the preferred notation is usually that interval notation. So in this case, how we would write that we exclude 0 is that we would write, okay, the lowest number, there still isn't one, so we go to negative infinity, and then we'd go up to 0. Now we're not including 0, so we use a parentheses. And then we also have all the numbers between 0 and infinity. So we kind of have these two disjointed parts of the domain, and we're joining them together, so we use this big U symbol, which stands for union. So we would read this as negative infinity to 0, union 0 to infinity. So in other words, the only number that we're excluding is 0. Another example where we might see an issue in our domain, something we have to look out for. Let's say we have the function a of x equals the square root of 7 minus x. Okay. So denominators introduce a problem with domains, right, which we can't divide by 0, like on the last one. In this one, we have to be aware that we can't take the square root of a negative number. So if you remember, the square root means what number times itself gives us this number. if we try to take the square root of, say, -4, we're saying what number times itself gives us -4. And 2 doesn't work because 2 times 2 is 4, of course. -2 doesn't work either, though, because -2 times -2 is also 4. So there's no real number that satisfies this. And this is where you start getting into like imaginary numbers or complex numbers, if you're ever studying that. But just in terms of the real numbers, there's nothing that satisfies this equation. So we have to make sure that what's inside of the square root is greater than or equal to 0. Okay. So this means that 7 minus x must be greater than or equal to 0. So we're just looking at the part inside here. So what we're saying is that this term, this expression, the 7 minus x, when we evaluate it, it has to be 0 or something larger. Okay. And we'll get into solving these kind of what we call inequalities. So they look like equations, but they're with something other than an equal sign. We'll get into solving these again in a separate video, but they mostly just work exactly the same as an equation. So we can add x to both sides here, and we'll get 7 is greater than or equal to x. And thinking of it the other way, this means x is less than or equal to 7. So x has to be a number that is less than or equal to 7. Okay. So in the interval notation here, we would write, so 7 is the largest number that it can be. So 7 will be the second number. And notice I'm using a bracket here instead of a parentheses. This is because 7 can be one of the numbers, right? So in the previous example, 0 was excluded. 0 could not be put into the function, so we use the parentheses to indicate that. When we use the bracket, that indicates that that number can be put into the function. And then on the other side, we just have negative infinity, right? So it can be any number between negative infinity and 7, including 7. Now, interval notation is the preferred method to write the domain in many cases, but just real quick, I want to show a couple of other options that we have here. One is called the set builder notation. So this is just so that you're aware of it in case, you read it somewhere. The set builder notation, this is writing the domain as a set, because the domain is a set. It's a set of numbers, a set of the x values. So we usually write sets with braces. And the way we write this is that we write that it can be any x such that, so this bar right here means such that. In this case, it would just be x is less than or equal to 7. Okay. So we write it as x such that x is less than or equal to 7. So you write the variable that you're using on the left side of the bar here, and then you write the inequality on the right side of the bar here. Okay. And then also sometimes some people like to draw these on a number line, so it'll help you visualize exactly what the x values are that are allowed. So say we'll start at 7, since that's the limits of our domain here. Etc., right? So the way we would draw this on a number line is, because 7 is included here, we'd put a closed circle at 7, and then we would draw an arrow through the rest of the numbers, and then we'd put a little arrow on the end of it saying that we're going to go this way forever. So this is all the numbers that are less than or equal to 7. If 7 was not included, we would instead use an open circle to represent that. So these are some alternative notations, but in general, the interval notation is preferred.